Disruptive. So I'm Mark Tesaro. I'm the interim lead for the point-of-care ultrasound program at the emergency department at Sick Kids. And we're going to go over a simplified version of the physics and knobology for point-of-care users. It's supposed to be like real-life physics and not exhaustive theoretical. And it's important for me to give a shout out to people who trained me and gave me some of these awesome slides that we're going to use. Eitan Dickman and Lawrence Haynes at Maimonides Medical Center in the deep south of Brooklyn, New York. So we're just going to talk about the basics of the physics and all the knobs you'll encounter to know which ones you need to care about at the start and which ones you don't. And the POCUS fellows are going to outgrow this talk very quickly. But that's what we're around for. So when you first approach the machine, that first day you're going to use it, this is intimidating, right? Just like how if you had never seen anyone drive or pretended to drive yourself as a child, this can be pretty intimidating. Knowing what's an important button, what gets you on the road and driving, what are the basics and what are the bells and whistles is really hard to know from just looking at that keyboard. So we'll try to boil that down for you. And you're going to hear me say over and over again that I don't like thinking about ultrasound as sound. I like to think about it as percussion. I like to think about it as a pressure wave because it makes a lot more sense when you do. But that's all that sound is. Sound is a pressure wave that your vocal cords, if you're talking about sound in speech, they vibrate up and down like a speaker does. They hit molecules within the air. They force those molecules to move outwards, hit other molecules until they reach a transducer, which is someone else's eardrum, and then those molecules cause the eardrum to shake. And in medical ultrasound, you're getting the same effect, but the speaker and the receiver are the same device, the same crystal or membrane within your probe. And this is all based on frequency. So no, we cannot hear ultrasound, and even Batman here on the ultrasound machine can't hear medical ultrasound because it's that much higher than the frequencies that are audible to humans or to other mammals. We are very human-centric when we talk about things, so the definition of sound is, for us, just what we can hear up to, which is 20,000 hertz or 0.02 megahertz. Which is a couple of orders of magnitude lower than the values we talk about in medical ultrasound. The lowest we ever really use in medical ultrasound is 2 megahertz. So like a couple orders of magnitude higher than we can hear. And then there are probes. We have a probe that goes up to 20 megahertz, but the majority of stuff you'll see is between 2 to 15 megahertz. And in terms of how the machines make this sound, they depend on a age-old quality called piezoelectricity, which just means pressure electricity. So there are certain substances in the world that if you apply pressure to them, they will spit out electrons. Or if you apply electrons to them, they'll spit out pressure, kind of work bidirectionally. Often they're types of crystals, and the original version of this that made it into electrical devices was quartz. So quartz watches, if you wound a spring that put pressure on a crystal, it could generate electricity for you. So the first digital watches operated under that before they all became battery powered. And so you take a crystal that has these properties, you apply electrical current to it, and the surface of it will vibrate, produce a mechanical wave that can go into tissues until it hits a tissue reflector. And if your vibrating crystal shuts off just after you've done that and just waits, then that wave will come back, hit the crystal, it'll spit out electricity back to the machine, and then it's the machine's job to process that and turn it into a picture. And the very first ultrasound machines that used what was later given the term A mode, they didn't produce a visual picture for you. There was no grayscale, like, here's a picture of what's inside. They produced like an oscilloscope tracing of a dot that would show up, and you had to write it down on graph paper and say like, oh, I think that means there may be a stone. And there were early computers that tried to do some of this work. And then there's really the computer revolution of the 70s and early 80s that allowed like such clear pictures to be generated from that information. So what the machine's doing when it sends that echo, and then it stops and waits, and then it gets hit by a pressure wave and generates another bit of electricity, is it's operating on a very simple assumption about the speed of sound, the speed of these waves within an average of body tissue. So if you were to grind a human up and say, well, how fast does sound travel in that medium? That's what the machine is using to say, I sent out a wave. I know there's a set speed in which it's going to go in and come back. So I can take time from when I produced the pressure wave until I heard the echo, and that is distance. So time until echo for the machine is the location of a pixel that it's going to show on screen. And it also knows when I sent out that wave, I did so with a certain amplitude. What was the amplitude of the reflection I got back? And I'm going to use that amplitude to say how bright that pixel should be. And just for information, I believe the speed of sound within human tissue is like 1.5 kilometers per second. In terms of pixel brightnesses, you've got like 256 grayscale units on most machines in terms of how bright they can range between. The bottom picture is how a lot of us have been conditioned to think about waves from physics books. And I always thought, that meant that when a wave was propagating through air or tissue, that there were things going up and down like this. And there are, when there's some kinds of materials, this is the way that a wave in the surface of water looks. So we can conceptualize some waves that way. It's not a great way to conceptualize what molecules are doing when you apply pressure to them with ultrasound. The top way, this idea of compressions and rarefactions, is a bit of a better way to understand what's happening, which is that molecules are being forced to push into other molecules. They're getting some inertia as they do that. I push them out, they run into other things, that they slow down, they transmit energy to the next molecules, which then bounce out. And the bottom waveforms are just ways in which we can understand the principles of these waves easier. We can understand concepts like frequency and wavelength and amplitude in this graphical form better, but there aren't a lot of molecules doing that tracing when you are using medical ultrasound.